Bismillah ar-Rahman ar-Rahim. So we started last time talking about chapter 3 or the transport layer. We talked about the main functionality of the transport layer, the fact that it establishes an end-to-end communication between two endpoints, two application endpoints, whether this is peer-to-peer or client and server and so on. We also talked about multiplexing and demultiplexing and for the case of connection-oriented or connectionless. Today, inshallah, we're going to cover the principles of reliable data transfer. This is one of the most important topics on the internet. The fact that your protocol needs to provide some guarantees on the delivery of data. So we'll start from no guarantees whatsoever. We'll start from the fact that our protocol doesn't need to address any kind of reliability on the information. Of course, this assumes implicitly that the channel or the communication channel that we use is reliable by default. So we don't have to provide any extra verification or any extra handling to make sure that the communication is reliable. Or we need some kind of reliability. The reliability has certain levels. Depending on the assumptions that you make on the channel, you need to provide one or two or all these levels, which means that you need to be like TCP, which means that 100% reliable, or you probably need to address reliability for certain levels, but not everything, and so on. So we'll go gradually now. So in terms of the reliable data transfer, of course, is important, not just from the transport layer perspective. Reliable data transfer is important in general as a concept. It's very important and is one of the most important topics. And it can be done in any layer, basically. Currently, the internet architecture uses best effort for network layer and uses some kind of data reliability in the transport layer. That's why we discuss the reliable data transfer as part of the transport layer. But that doesn't mean that this is the only layer where you can provide reliable data transfer. Reliable data transfer is just a concept that you can provide in any layer depending on your network architecture. Okay, so sometimes data link layer for certain types of networks needs to be reliable. We need to provide some reliable data transfer in the data link layer. In some cases in the network layer. In some cases in transport layer. So the network architecture and the type of media that you are dealing with dictates the level of reliability that you need to provide. So the transport layer, in terms of provided service, it needs to provide reliable data transfer, but that can have different forms. That's what we will talk about today. It needs to provide reliable data transfer over unreliable channel. Okay? So if the channel itself is unreliable, there is a high probability of error. Okay? So we need to do certain implementation of the transport layer to compensate for the fact that the channel, the communication channel itself, is unreliable. For example, if you have like wireless, if you have any unreliable channel end-to-end, or some of the routers that you use throughout the end-to-end path are not reliable, they don't provide any guarantees, or they have some traffic jams, or they have small queues, or they have so many things. In general, the end-to-end communication is unreliable. So the transport layer now needs to do some extra things in order to make sure that the service that it provides is reliable in terms of data transfer. So as we said before, reliability itself has multiple forms and multiple levels. And the characteristics of the unreliable channel will dictate the complexity of the transport layer protocol to provide reliable data transfer over unreliable channel. So for example, I can assume that my channel is error-free. Okay? So if I make this assumption, I don't have to check for errors. Okay? So I don't have to verify that the information that I receive is in error or not. I don't have to do that check. If I assume that my channel is lossy, which means that it could be error-free, but I can lose the entire packet or the entire segment. Okay? In which case, how do I compensate for this? First, how can I detect that if the packet is lost, that it's lost? Okay? And when I detect this, what do I do in order to react to this? Do I do some do I do some retransmission? Or what do I do exactly? Okay? How do I handle this? So again, the amount of reliable data transfer done from the implementation point of view of the transport layer is dictated by the characteristics of the unreliable channel. Whether the unreliable channel is error-free, is lossy, is lossless, but it could have some could introduce some errors, but it cannot lose the data, something like that. Okay, so the more assumptions you make on the unreliable channel of communication, the less work you need to do on the transport layer. So if the channel takes care of everything for you, then you don't have to do anything. Okay, يعني what we are saying now is up in the air, but it will be very clear when we start talking about particular examples. So we will assume perfect situation at the beginning. Channel is error-free, is lossless, everything is good, okay? And then we will try to see what the transport layer protocol would look like. And then we'll start to loosen up the assumptions that we make on the channel. Now the channel is not perfect. The channel can introduce some errors. What do we need to do extra? And we need to use this logical thinking in order to gradually and incrementally complicate the implementation of the transport layer to provide reliable data transfer over the unreliable channel. Okay? So if we assume that we have unreliable channel, then we need to provide reliable data transfer protocol over unreliable channel. Okay? Reliable data transfer in many cases, as you can see here, the transport layer protocol, what it does is that at the sending side, you have some information in the application layer. This information will be segmented, okay, into pieces. We call it segments, and these segments will need to be transferred over the communication channel to the receiver. Okay, so if we need to do reliable data transfer, chances are this is bidirectional, as we can see. This is going up and down. Why? Because to provide reliable data transfer over unreliable channel, you probably need to retransmit, which means that when you send something to the receiver, there has to be a way or a mechanism for you to make sure that it arrived. It's similar to the mail service. You have a basic mail service. When you send the letter, the mail office does not provide any guarantee. And the receiver on the other side is not expecting anything. Is there any guarantee that the mail will arrive on the other end? The mail office does not provide any guarantee. Or there is a more reliable mail service that before you send the mail, you need to make sure that the person on the other side is registered and the person on the other side is notified that I sent something, and when it arrives to that person, some notification comes back to you to say that this mail has arrived, and so on and so forth. So that's the reliable data transfer. So to do this, we have this bidirectional, although this, the direction here is one, so either you go down or you go up, like here. This is at the receiver side. Of course, this is the sender, and this is the receiver. Okay? But here, to provide reliable data transfer, you probably need to do some verification that the segment has arrived on the receiver side. Okay? So this, you have reliable data transfer send, and this is supposed to be an interrupt that the application layer gives to you. So in the application layer, there is a buffer, and the application layer will say, okay, I have some data to send. This is actually sent as an interrupt to the transport layer protocol. And the transport layer protocol will then pick up from the buffer, it picks up the segment, and then will start transmitting that segment through the communication channel, reliably or unreliably. If we're talking about reliable, then when we send it, we have to make sure that it arrived, which means that we have to wait for acknowledgement or some verification and so on. Okay, on the other side, of course, on the other side here, when we send, the receiver will receive a reliable data transfer receive, which means that, again, it's an interrupt from the lower layer, in this case, from the network layer, that there is a packet that you can now receive and deliver to the application layer. Okay? So when we receive it, we look at the port number, and then we send it up to the application layer depending on the port number. So that's this path. On the other side, because we're talking about reliable data transfer over unreliable channel, we need to send some verification, which is done as a form of acknowledgement. Okay? So we send unreliable data transfer, okay, because this unreliable data transfer does not require a verification in that case. So, and we'll talk about this case. If the acknowledgement itself is lost. So if we send unreliable data transfer, so we assume that that channel is reliable from one direction, which means that the possibility of losing the acknowledgement is almost zero. And we'll talk about the case that it's actually bidirectionally unreliable.
I think I'm not understanding unreliable channel.
Yeah, the concept of unreliable channel, this means that this channel is, there's no guarantee that this channel will give to you on the delivery of any information. Which means that the underlying communication channel is unreliable, which means that there is no guarantee on the delivery, which is typically what happens on the internet, because as we all know, what we are supposed to know, that the network layer is best effort. It does not provide any guarantees. It's connectionless. IP is connectionless, and it's best effort. Okay? Which means that by default, the network layer is unreliable. Because when you send a packet, the routers, they work by default as best effort. Yani if the buffer inside the router is full, what does it do? It drops the packet. If the packet arrives in error, what does it do? It drops the packet. Does it perform retransmission? No, it doesn't. The router itself will not do any retransmission. Okay? So by default on the internet, the network layer is unreliable. So that's what we mean by unreliable channel. Channel here is an abstract terminology of the underlying communication infrastructure. All the underlying layers, for me, is unreliable or reliable. If we assume that it's reliable, okay, which means that all the routers guarantee delivery and everything, then the transport layer doesn't have to do anything to provide reliable data transfer. Because we send anything on the channel will guarantee that it arrives on the other side. It arrives error-free. Not only it arrives error-free. Okay? So this is an idealistic communication channel, which does not exist on the internet, for sure. So we know that the underlying layers are by default unreliable, which means that the transport layer needs to provide some reliable data transfer. And as we said, the amount or the level of reliability that the transport layer can provide is dictated by the characteristics of this unreliable channel. Because some unreliable channels are lossless, but they can introduce some errors to the packet, which means that the packet is guaranteed to arrive, but it may have some bits changed.
But this is the data link layer. The checksum will...
This is general. We're talking in general. Okay, in general. This can be introduced in the network layer as well. Okay, so the packet may arrive, but there may be some bits changed. If the bits, for example, are changed in the network layer header, it will not be checked. It will not be detected by the data link, and the data link may actually send it up. And now in the network layer, it may discover that there is some bits changed in the packet itself. So the error detection happens at the network layer, in which case the router may drop it. In any case, the channel may be lossless, but it produces some error. Or maybe it's lossy, but error-free. Or both. Ideally, we need to provide reliable data transfer in case of all these types of errors. But as we will see, the more we assume on the unreliability of the channel, the more the transport layer will be more and more complicated, as we will see. Okay? So send will correspond to reliable data transfer received, and then because the channel is unreliable, so we may want to send some confirmation in a form of acknowledgement, which will be triggered here by the unreliable data transfer send, but this is from the lower layer. Okay? It's coming as an entry from the network layer. Then the transport layer will receive this, will recognize that this is an acknowledgement, so it needs to check whether this acknowledgement is for a data that I send. If they match, then everything is good, and I need to move to the next segment. Okay, so these are and if here I receive a data and there is no error and everything is good, then deliver data, which means that send the data to the upper layer. So these are the four major APIs or functions, if you will, that are provided by the transport layer. So RDT send is coming from the application layer at the sender side, okay, and UDT send is coming from the lower layer, okay, and on the other side of the receiver there is the RDT receive, and they deliver data to the upper layer.
RDT, because here sender is knowing that it is unreliable.
Yeah,
He
so
should also say RDT underscore send, but while receiver side he is saying RDT underscore receive. So that's why slightly confusion here. So why not both side RDT underscore?
because as we said, the acknowledgement is sent with the assumption that the channel is reliable. It's reliable, which means that it's unreliable data transfer sent for the acknowledgement. Why? Because as we will see later, if the acknowledgement itself is lost, okay, there is an indirect way that I will detect the loss of the acknowledgement, and we will see how we do this. But in general, when I send the acknowledgement, I don't have to wait for acknowledgement that the acknowledgement has arrived. You see what I mean?
Yeah.
So here, reliable data transfer means that when I send, I need to wait for acknowledgement. That's why it's called reliable data transfer. So it's a two steps procedure. Reliable data transfer means that when I send, I have to wait for acknowledgement. But when I send an acknowledgement, I don't have to wait for acknowledgement. Otherwise, I'll go in loops, right? So I don't do that. But we will see cases that even the acknowledgement can be lost. We'll do that.
It will not depend on the type of the protocol.
Yes, that's why we said that reliability can be done in levels. And we'll see that actually the two protocols that we'll study, they are taking the two extremes. UDP assumes everything is perfect, whereas it's not, right? And TCP assumes everything is bad, and I need to do everything. And that's also bad. Okay, so the two extremes are usually for certain applications, neither of them is actually good. Okay?
So one question last. So why sender side is UDP, why he is not?
So the way we will go about designing the transport layer protocol is using finite state machine. Okay, so finite state machine is a concept that you probably have studied in some courses before. And it's basically, when you design any system, you design the system in terms of states. You say that this system can take multiple states, okay? And when the system is in this state, it interacts with the environment based on certain events. So when I'm in this state and there is an event, then I need to do something. And in doing this thing, I might have to transition to another state. That's what it means, basically. So we transform the system into, or the design of the protocol into states, okay? There is an initial state, and this initial state is usually the initial state of the system, and then I will wait for something to happen. So we'll talk about how we model this, how we model the transport layer protocol using this concept. If there is an event, then based on this event, I do a certain action, and then I may or may not have to transition to another state. Okay? So for example, if I'm waiting for acknowledgement, and there is an event that acknowledgement has been received, then I can do something, which means I process this acknowledgement, and based on processing the acknowledgement, I may have to transition to another state. Okay? Which means that I'm not anymore waiting for acknowledgement. So I have to wait for example, like another segment coming from the application layer. Okay? So that's how we design the transport layer protocol using the finite state machine. You have a question? Okay. So of course, sometimes I don't have to always transition from one state to another, right? So maybe based on certain event, I will stay in the same state. So we'll see what type of events do I have and what type of states do I have. So initially we will consider only unidirectional data transfer, assuming that the channel is perfect. Okay? So we don't have to do bidirectional acknowledgement and whatnot. We don't have to do anything. Everything is unreliable. From the transport layer point of view, it's unreliable. Okay? Because the channel is perfect. So the assumption here is that we cannot lose anything, and everything arrives correctly. There is no possibility that we send a segment and it arrives in error on the other side. There is no that possibility. Then, gradually, we will loosen some of these assumptions and we'll start to complicate the implementation of the transport layer step by step. So if the underlying channel is perfectly reliable, all we need to do is just wait for a call from above. Okay? So this is the only state that I have. And the state is wait for a call from the application. When I get this call, all I need to do is just to send the packet. So I create the packet. Create the packet here means that I add the header. I add the transport layer header. And then I do a UDT send, because in that case, it's unreliable. And I keep myself in the same state. I don't have to wait for anything else. This is the only state. Okay? It's because everything is perfect, channel is reliable, so I don't have to do anything specific. Right? At the other side, wait for data from below, in that case. This is the receiver side, or the reverse operation. And again, when I receive, I don't have to do anything to handle any possibility of error, because again, the assumption is that channel is error-free. I don't have to send anything back, because again, the assumption is that nothing can be lost. Okay? And then deliver data to above. Very simple, right? One state here, that's it.
Deliver data to user?
Deliver data to the application. Okay? So in here, I have to do demultiplexing. The demultiplexing that we talked about. All I need to do is just to check the port number, and deliver it to the proper application. So in terms of multiplexing and demultiplexing, we know that from last time.
It will be receiver side, you will use RTD. Receive.
Yes. So it assumes here RDT received because it's reliable by default. Okay? So now, underlying channel may flip an error. So we will complicate it one step by saying that the channel now, it cannot lose anything, but it can only introduce some bits in error. Okay? So there's no possibility for loss. But there is a possibility that the channel may change some of the bits, which means that ones become 0 or 0 become 1. That's it. So the question is how to recover from errors in that case. Because the checks for error will happen at the receiver side, right? So we send everything correctly, hopefully, from the sender side, right? But the error checking happens at the receiver side. So how would the sender know? There are multiple ways to do this. And one of them is that the receiver, if it receives everything correctly, then it sends positive acknowledgement. And when it receives something in error, it sends negative acknowledgement. Okay? There are multiple ways to do this, but that's one of them. And we will see later on that we can eliminate the negative acknowledgement altogether. So we'll see how to do that. When the sender receives the negative acknowledgement, which again, it cannot be lost, right? Because the assumption is that channel cannot lose anything. Then the sender will send the same packet again. Okay? So we can recover from this by just adding acknowledgement and negative acknowledgement. That's it. That's all we need to add. Okay? So let's see what is the reflection of this on the finite state machine. So now I need to account for acknowledgement and negative acknowledgement. Okay? So it's not that I send and that's it. No. When I send, I have to wait for something. So now there is wait from above, wait for data from above, and wait to receive acknowledgement and negative acknowledgement from below. So I know that I cannot have only one state. I have two states now. Any questions?
The receiver will send only the positive acknowledgement or negative acknowledgement?
Which the receiver, the receiver will send positive or negative acknowledgement, yes.
One of them.
Yes, of course. Based on whether the data is arriving correctly at the receiver or the data is arriving in error. Because it will arrive, but it will arrive maybe in error or correctly. Okay? So here I have two states. Okay? When I start with this initial state, and the initial state is marked by this dotted arrow usually. And sometimes we use this arrow to initialize, to do some initialization, as we will see later. Okay? Just to mark that this is the initial state of the system. So when I start, I will wait for a call from above. Basically, wait for any data to arrive to the socket buffer. That's what it means. If there is any data arriving to the socket buffer, then I need to pick it up, and then I start to send it. When I send it, the assumption is that the channel may actually introduce certain errors, in which case I need to I need to wait for acknowledgement or negative acknowledgement. So at the sender side, when I send in that case reliable data transfer send, okay? When I receive the reliable data transfer send from the application, this is the action. So again, always on top, event. Here, under the line, the action that you take, or the actions that you take, okay? So when I receive this interrupt from the application layer, I perform two things. I add the header to the data, and and how can I check for errors? Using checksum. So I add the checksum to the header. And then I send. When I send, I transfer to the next state. In this next state, I will wait for acknowledgement or negative acknowledgement. So I have two states. Or I can split this into wait for acknowledgement and wait for negative acknowledgement. But usually, you can actually design your finite state machine in multiple ways, and it's up to you. As we will see later, we can combine all of them in one state. But again, the events and everything will be more complicated. So it's up to you, really, how you divide the system into multiple states. So wait for acknowledgement or negative acknowledgement. If I receive the incoming packet and isNAC is true, which means that what's coming is negative acknowledgement, this is an indication of error. So in that case, I need to send again. When I send again, I will be in the same state, because this is retransmission, and now I will wait for another acknowledgement or negative acknowledgement. If I receive positive acknowledgement, then everything is fine, okay? Then go here and get the next packet. Wait for the next packet from the application and send it when you receive.
It should be
So,
should be RTD in the sender side when I send the packet, not UTD, because I will wait for acknowledgement.
here,
Yes. UTD send packet. When I send the packet, I will send it in RTD protocol, not UTD, because I will wait for acknowledgement.
yes, but يعني from the okay, again, from the higher layer point of view, it's RDT send, okay? And then this is split into two directions. There is UTD send and UTD receive. Both of them are RDT send. يعني RDT send from above will be split into two UTD send and UTD receive. That's what this is all about. So you divide the RDT send from above into two bidirectional. Okay, each one of them is UTD or UDT. Sorry.
But now the channel is
Unreliable. Yes. Yes.
And I know that there will be an error in the channel. So why I don't have RTD real data protocol to receive the acknowledgement?
Here.
Yes.
The same is like earlier, no? Earlier also sending it was UDT, while receiving it was RDT.
It was just a terminology from the perspective of the of this finite state machine. It's just a terminology. So the RDT here is divided into UDT send and UDT receive, because the RDT send corresponds to RDT receive on the other side here. You see that here it's so RDT send is received as an event RDT receive. In any case, this is just a terminology. It's just a naming convention. Okay, يعني in any case, if you put this in the exam RDT, I will not pick on that. There's no problem with this. The important thing is the concept itself. The concept itself is that it's reliable data transfer from the application point of view. When the transport layer performs this reliable data transfer, it sends one message to the receiver, and it waits for acknowledgement. Okay? Each one of them is unidirectional. Okay? If you want to call this RDT send, I will not disagree with you, honestly. Okay? Type.
Sir, one more question, sir. That at receiver side, this RDT receive packet and is
Here.
NAK. So why NAK? It should be AK, no? That acknowledge.
Here. Is ACK is here. If I receive a negative acknowledgement, then I resend and wait for it. If I receive acknowledgement, which is this case, I don't have to do anything. This means that whatever I sent has arrived. Okay? So I don't have to do anything. This is like phi. I don't have to do any action. But I need to update the system state into the initial state. Wait for packet to come from above. Okay? At the receiver side, remember, it's just again, I can do this in two states or one state. Here it's done using one state. So wait for call from below. So when I receive a packet from below, then I need to check first if it's if there is any error with this packet or not. So all I need to do is just to check if it's corrupted. Corrupted here means that I need to generate the checksum and match the checksum with the one that was sent from here, which is a very simple operation. Okay? So when I do this, I will figure out whether this packet is corrupted or not. Okay? Corrupted means that it's an error. So if I receive a packet and it's corrupted, which means that it's an error, then what I need to do is that I need to send negative acknowledgement. I need to send negative acknowledgement in that case. And if it arrives and it's not corrupt, which means that it's error-free, then I need to send positive acknowledgement, but before this, I need to deliver the packet to the application. Okay, so I do two things here. So yeah, it makes sense that it's one state, because the only thing I wait for is for a packet to come from below. I don't have to wait for anything else, right? So it makes sense that it's one state.
But how does the second loop?
Here? ما هو you have two possibilities. Either the packet that arrives is in error, or the packet that arrives is error-free.
If there is recurrent, yes?
Sorry?
If there is error, it will be the first loop. There is
This one? Yes.
If there is no error, so it needs acknowledgement.
It needs to send a positive acknowledgement.
So there is another finite state.
No, because if it arrives and there is no error with it, I need to do two things. I need to deliver it to the application and send positive acknowledgement. Both. I need to do two things. Because it arrives error-free, I can deliver it correctly to the application. Okay? And also, the sender is waiting for verification that this has arrived with no error. So I need to send an acknowledgement. So I need to do two things. Okay, of course, any transport layer will have those two finite state machines, both, because every transport layer can work as a transmitter and a receiver. In fact, every socket connection has both, because it's bidirectional, right? So the TCP has bidirectional communication by default. So both the finite state machines will be working simultaneously, right? Type. So, oops. This is based on the fact that, again, this slide describes the operation. If everything is correct. If everything is correct, so when I send the packet, it arrives with no error. So it triggers this part, which means that it goes up to the application and I send positive acknowledgement. For the case of, so that's another part of it. For the case of error, what happens is that when I send, the channel in the middle introduces some changes to the bits. So it arrives corrupted. When it's corrupted, I need to send negative acknowledgement and wait for the same packet to come again. which means that I will wait for retransmission of the packet. So, so this is the scenario if the channel cannot lose anything, but the bits in the packet itself may change because the channel is unreliable. What we did not address here is if the acknowledgement itself is corrupted, right? On the way back, this acknowledgement or negative acknowledgement is on its own corrupted. Okay? So we did not address this issue. So even when we assume that the channel is unreliable now, it's unreliable from one direction, but it's reliable in the other direction. So we assume that nothing can be wrong with the acknowledgement and negative acknowledgement. Okay? So we did not address this issue. So we'll try to complicate this even more. So again, this is the same. So nothing is new here. This is just for all the cases. When I send the acknowledgement, it goes out here, and this is what gets triggered in the case of error, and this is what gets triggered in the case of no error. So if no error, I receive here acknowledgement, which means that I don't have to do anything in that case. I just got a confirmation that it has arrived, so I don't have to do anything. So what happens if the acknowledgement or negative acknowledgement is corrupted? So we have an implicit assumption here that the backward channel is reliable, which we didn't say that. If it's unreliable, why the backward channel is reliable? Okay, so there is something missing here. So in that case, the sender will not know what happened, because if the acknowledgement or negative acknowledgement arrive in error, the sender will be forced to drop it. Will be forced to drop the acknowledgement. It will not know whether this acknowledgement is a confirmation for the packet or not. Okay? It can assume that it's an acknowledgement, which means that it's not necessarily true, or it can assume that it's negative acknowledgement, which also not necessarily true. So it can work incorrectly. Okay? Because if the acknowledgement or negative acknowledgement is corrupted, I won't be able to decode what's inside the packet. In which case, the sender cannot just retransmit, and that's it, because this will be a premature decision. I don't know whether this is acknowledgement or negative acknowledgement. And if it retransmits the packet, assuming that maybe I will be conservative. Okay, so if I cannot recognize, I will assume that it's negative acknowledgement. So retransmit. Well, if it's retransmission, this means that the receiver may have duplicate packets. And what the receiver does now for duplicate packets, it will send it up. So the application will get to, the application itself will work incorrectly, because the application will receive 2 duplicate packets. And this will cause lots of problems in the application. Okay? So we need to address this issue. So if the sender retransmits, so the way to handle this is that if the sender retransmits the current acknowledgement and negative acknowledgement, it needs to at least add a sequence number to each packet. Why? Yes, because if I send 2 packets with the same sequence number, this will be an easy thing for the receiver to detect that this is indeed duplicate packet. So it will not send it to the application. Okay? So this is good, right? So at least if I put any sequence number in the packet, the receiver will be able to tell whether this is a new packet that's arriving for the first time, or it's a duplicate packet, in which case the acknowledgement or the negative acknowledgement that I sent did not arrive correctly to the sender. So if I have this sequence number, then I can detect duplicate packets. And in which case, the receiver will discard this packet if it's duplicate. So in that case, the sequence number, because for every transmission there is acknowledgement. For every transmission there is acknowledgement. So the only possibility is that only one packet will arrive incorrectly, in which case I need to distinguish between only 2 packets. Okay? So I cannot have multiple packets because every time I have to wait for acknowledgement before I send the next one, which is basically, if you have studied before, this is stop and wait. صح? This is basically stop and wait. For every packet, I need to receive an acknowledgement. So in that case, how many sequence numbers we need? This is 455. How many sequence numbers do we need for stop and wait?
It depends on the number of two.
هو احنا for stop and wait, yes, because for we don't send any new segment until we receive the acknowledgement for the previous one. Okay? So the state of the system can possibly be the current packet or the next packet. The current packet, I retransmit it if there is an error, okay? Or I send the next packet. And for the receiver, it knows from the sequence number whether this is a new packet or this is a retransmission of the previous packet. I don't have any other possibility because we will complicate this even more next and we'll see if we have multiple packets. But since we are waiting for acknowledgement for every single packet we send, we only need to distinguish between 2 packets only. We only need to know whether this is a new packet or a retransmission for an old packet. These are the 2 possible states. We don't have any other possibility. We will see بقى when we complicate this even more. طيب.
More than that?
Yeah. Still a long way to go. يعني لا احنا what we're trying to do now is we're trying to take some logical thinking into really designing the protocol layer, the transport layer protocol, in terms of providing reliable data transfer. That's how the designer actually thinks about designing this protocol. He or she takes some steps into complicating the protocol, and as we will see when we add بقى كمان flow control on top of error control, because now we're talking about error control. So the motivation behind go back N, which is the extension of stop and wait, is not related to error recovery at all. Okay? So error is handled by stop and wait very well. But there is a drawback in stop and wait, which we will see in a minute, that will motivate the thinking of go back in. Okay? But we're trying to take some simple steps into designing the transport layer protocol. So here, what I need to do is that the logical thinking is that now I need to have 2 sequence numbers. If this packet is 1 or 2, that's it. So 2 possible sequence number, which means that it's either packet 0 or packet 1. That's it. Because for packet 0, I will have to wait for acknowledgement before I go to packet 1. Okay? And if packet 0 I did not get confirmation, then I send packet 0 again. So it will be easy for the receiver to know from the sequence that it's either a new packet or it's a retransmission of the old packet. So that's how the sender looks like. This is nothing but a duplication of the previous one for 2 cases. Here, this part here is for when the packet is 0. And we do the exact same thing that we have done before. Okay? Except on the way back here, we don't actually go to this state. We go to the same state but for packet 1. That's the only difference. مفهوم هنا؟ So it's just a duplication of the previous one. For one side it's 0 and for the other side it's 1. That's it. Okay? And the one above is a mirror, because when I wait for acknowledgement, if I receive a positive acknowledgement, I have to go to wait for the application layer to send me packet 1. Okay? So instead of going here, I will go to the same state but for packet 1. مفهومة? So it's just a duplication of the previous one. So I actually repeated it twice, 140 and 141. It's easy, yani. When you think about it this way, it's very easy. And then the same logic applies, because here is the sender is nothing but just a duplication of the previous one for the two cases. It's actually up to the receiver to now distinguish between 0 and 1, to figure out that...
This is for stop and wait.
Yes, this is for stop and wait. That it's now the receiver needs to check the sequence number to figure out whether it's a new packet or it's an old packet. So if I'm waiting for packet 0 and I get packet 1, what do I do? If I'm waiting for packet 0 at the receiver side, okay, and I read and I got an interrupt and a packet arrived, and I check the sequence number in the packet is 1. First of all, when does this scenario happen?
When I send the negative acknowledgement and they receive it as positive.
لا مش كده. When I send a positive or negative acknowledgement, when I send a positive acknowledgement to the receiver, to the sender, that everything was fine, okay? Since and now I'm waiting for packet 0 to arrive because packet 1 has already arrived, right? But this acknowledgement arrived in error at the sender.
It flipped.
Yeah, some of the bits has flipped. So for some reason, the sender did not figure out that the acknowledgement that I sent is acknowledgement or negative acknowledgement. It's corrupted. So what does the sender will do now? Sender will have to retransmit. In that case, we'll have to when it retransmits the packet, it retransmits the packet with the same sequence number, which is 1. Okay? So now the receiver will receive the packet, and it finds that the sequence number is 1. But 1 has already arrived before, right? So what does it do? Drops it. It drops it. That's true. Okay? So that's how the receiver will figure out if it's new or not. There is another part to this which we will talk about. So again, this is just a duplication. Okay, so we agree on this, and we just need to know that when we have an acknowledgement for 0, we switch to 1, and when we have an acknowledgement for 1, we switch to 0. Those are the two possibilities that we have, because this is stop and wait, and we need 2 sequence numbers only.
You mean that if we have acknowledgement of 0 and we have it 0, we go to 1?
Yes. So these are the only 2 possibilities. This is the way to handle if the acknowledgement or negative acknowledgement from the receiver is corrupted. So we do need sequence numbers. But here, the possibilities that we have is that because we are waiting for acknowledgement for every single packet, so the only possibility is that we have 1 lost or 1 corrupted, which means that we only need 2 to verify whether this is 0 or 1. Okay? Because we will see in some other cases we don't have to wait for acknowledgement and we send multiple packets. In that case, we need more than 2 sequence numbers. We need more than that, and we will see this case.
One question means when it was initiated, and packet number 0 should come.
Yes.
But packet 1 is received at the receiver.
At the receiver, right.
So what will happen to packet number 0? Because it is saying that receiver has already received the packet 1.
Right.
So sender will not send
Yes. So the receiver needs to inform the sender now that somehow I have received the packet that you have sent, but I need to inform the sender that this packet has already arrived. I need the next one.
Yeah, so
something like that, right? So that's the other part that I talked about. So not only do I need to so when I receive the packet 1 while I'm waiting for packet 0, I will drop it. Not only do I need to drop it, but I need to inform the sender somehow that, I received this packet correctly, send me the next one. Okay? So in our case here, we will send an acknowledgement. And one thing that we have, that we can notice here is that the acknowledgement and negative acknowledgement do not have a sequence number. Okay? Do we need this or not? We will see. So this is from the sender side. It's just a duplication. From the receiver side, these are the possibilities. So again, we are splitting the states into waiting for 0 or waiting for 1, right? But now, let's look at that. The states now have become a little bit more complicated. So waiting for 0. So I have 3 possibilities now. 3 possibilities for each state. One is that I receive and the sequence number is 0, which I receive a packet, and the packet is not corrupted, and the sequence number is correct. If that's the case, then what I need to do is that, okay, I need to extract this packet, deliver the packet to above, send positive acknowledgement, go to this state. Logical, right? So I need to extract the packet, send it to above, and send positive acknowledgement. So hopefully when I send this positive acknowledgement, it will not be corrupted at the sender. But we will address this. The other possibility here is that it's based on this condition, really. Okay? So I receive the packet, which is the interrupt, the main interrupt. I receive packet from below, and it's corrupted. Okay? In that case, I don't have to check the sequence number because the packet is corrupted. So in that case, I send negative acknowledgement. Okay? This is the receiver side, which retransmit. Retransmit is from the sender side. So here, I will send a negative acknowledgement.
To myself?
Negative acknowledgement to the sender. This is the receiver. This is the receiver.
But when there's no connect between the finite?
ما هو الconnection is through the channel.
The initial line? The initial line.
This one?
From the sender, yeah?
The sender is in the previous slide. Here is the finite state machine of the receiver only.
So you will acknowledgement to negative acknowledgement to the sender.
Yes,
But
exactly.
why the arrow is back to the 0?
Because when I send a negative acknowledgement, I'm still waiting for this packet again. I expect the sender to retransmit because it arrived in error, right?
Yeah.
So I cannot transition to a new state. Now this is a finite state machine. When do you transition to a new state? When do you transition in the same state?
It's done.
Yes, exactly. If I receive positive acknowledgement. So this is this case.
Yes.
It's done. Okay? So I only transition when I receive the packet with no error and the sequence number matches. That's the issue now. If it's corrupted, I don't have to check the sequence number because it's corrupted, and I need to send a negative acknowledgement. As we can see here, the negative acknowledgement does not have a sequence. It only has a checksum because the sender now will need to check if this acknowledgement or negative acknowledgement is corrupted. Okay, and if it's corrupted, the default is to recognize it as a negative acknowledgement. It retransmits. But when it retransmits, the sequence number will allow us to work here. The sequence number will not match, and then we can figure out whether this is a duplicate or not. That's the trick. This is the only trick. So if the backward channel is also unreliable, this means that acknowledgement and negative acknowledgement might also be corrupted. So the sequence number is the key here. Through the sequence number, we will figure out whether this is a duplicate packet or it's a new packet. So the third case is when we receive a packet and it's not corrupted, but the sequence does not match. When does this happen? Because when we have sent acknowledgement here, when we have sent acknowledgement for this case, and we have transitioned to this state, the sender did not receive it correctly. It was corrupted on the way to the sender. So the sender retransmitted the same packet again. So this will trigger this case. Okay? Because the sender will send a packet, it arrives, no error, everything is fine, but the sequence number does not match. So this is the duplicate packet.
مثلا the sender sends 0 and we receive 1. This is the duplicate.
Yes.
I mean, this is the...
لا احنا we are waiting for here احنا we are waiting for packet 1 to arrive. Sorry, packet 0 to arrive.
0 to arrive, correct.
The packet that arrived has a sequence number 1. Okay? This means that before that we were in 1. We were in this state. Okay? We sent positive acknowledgement to the sender. And we have transitioned correctly to wait for packet 0. But when we send the acknowledgement, the sender did not receive it correctly. So the sender decided to retransmit the same packet 1 again. But we were waiting for packet 0. Okay? So we will consider that this is a duplicate packet. Why can't we recognize that this is a new packet? Is there any possibility for us that we are waiting for 0 and 1 is actually a new packet? There is no possibility. There is no such possibility because, again, here we wait for acknowledgement for every single packet that we send. And because we assume the channel cannot lose any packet or acknowledgement. Until now, we did not assume that the channel can lose anything. Until now. Right? Until now, we did not introduce the assumption or the hypothesis that the channel can lose anything. The channel cannot lose anything, neither the packet nor the acknowledgement. We did not introduce this yet. Okay?
We are dealing with errors only.
Yes, here we are living only with a channel that may change that may corrupt the packet only. Corrupt the packet or corrupt the acknowledgement or negative acknowledgement. Okay? So here, if we have 2 sequence numbers, we can live with that. Only with 2 sequence numbers, we can live with that. Okay? Because we can, through these 2 sequence numbers, we can figure out whether this is a duplicate packet or a new packet. These are the 2 possibilities that we have. And because we always wait for acknowledgement, and because we cannot lose this acknowledgement, we only need 2 sequence numbers. That's it.
Professor, so what happened in the third case?
Here?
Yeah, I send the acknowledgement.
Right. Fine here. Which one?
If the sequence number is different.
Right, here.
Yeah.
Okay.
So let's send
Here. Here, I received a packet from the sender, a new packet. Okay? And this packet is not corrupted, which means that the packet arrived correctly. But when I check the sequence number, it's 1. But here, the state is that I'm waiting for 0, not for 1. So when does this scenario happen? Because the acknowledgement that I have sent previously to the sender did not arrive to the sender correctly. So the sender decided to send the same packet again, which is packet 1. But for me, packet 1 has already arrived. Okay, so this is the discrepancy. So in that case, what I need to do is that I will discard. Definitely, I will discard this duplicate packet. But what I need to do here is that I need to send an acknowledgement because the packet arrived correctly. I will send an acknowledgement. Hopefully, by this time, when the sender receives this acknowledgement correctly, okay, it will send the next packet, which is in that case packet 0, which is what I'm waiting for. If it does not happen, then the sender will again send a packet 1. So this state will be triggered again. So I will keep looping in this case until I send the acknowledgement and the sender receives it correctly and it sends packet 0, which is what I'm waiting for. When I receive packet 0, then and only then I can wait here. I can go to this state and take packet 1. So here the discrepancy. While I'm waiting for packet 0, you cannot send me packet 1. While I'm waiting for packet 1, you cannot send me packet 0. That's why I have 2 states. So the 4 states in the sender and 2 states in the receiver. Okay? So until now, the assumption is that the channel cannot lose anything, can only introduce errors.
Doctor, one question here. Sorry. We are waiting for 0 and we received 1.
Yes.
But we said, okay, we received 1 and we acknowledge and said positive feedback also that it is a 1.
I'm just sending an acknowledgement. I'm not saying that I received 1 correctly. I'm just sending an acknowledgement. And as we said here in this case, we're not sending any sequence number in the acknowledgement or negative acknowledgement. We're not sending any sequence number. Okay? This is very important to...
Is this case what happened exactly in the wire network?
No, because in wired network, we account for errors. We account for packet loss. When does this happen? Because we are on the internet. Packet loss, even for wired, when does packet loss happen? When the packet arrives to the router and the router is jammed, is full, it drops the packet. Because again, the network layer is unreliable. The network layer is best effort, is unreliable. If the packet is lost, then the transport layer needs to do something about it. Okay? Go ahead.
When you are waiting for 1, for packet 0, sorry,
Mhm.
we receive 1.
Mm-hmm.
The receiver will send an acknowledgement or a negative acknowledgement?
Acknowledgement.
Acknowledgement?
Yes, acknowledgement
Then
here.
it's-
Yeah, it only sends a negative acknowledgement if it's corrupted. Okay, if it's corrupted. If I'm waiting for packet 0, okay, and I receive packet 1 corrupted, same thing. I will not trigger this in this case. I will trigger this.
Yeah.
I will send negative acknowledgement, which again will trigger the sender to retransmit. If it arrives correctly, but the sequence number is so here, what we're trying to say here is that the only way we can transition to the next state is when the packet arrives, there's no error, and the sequence number matches. Because otherwise, we will consider this as a duplicate packet, and we discard. That's what it means. Okay? So, next, if we introduce the assumption that the channel introduces any kind of error, any kind of loss, packet loss, what is the only technique to account for packet loss? Logically. ها؟
Acknowledgement.
ما هو acknowledgement. Okay. ما هو packet loss معناها ايه؟ I sent something and it's lost. Okay, so what do I, يعني how can I figure out that it's
I'm
lost?
waiting for send.
Because برافو عليك. If I'm sending something, because here the assumption is that when I send something, I will receive acknowledgement no matter what, because there's nothing can be lost, neither the packet nor the acknowledgement, right? But if the channel introduces some loss, which means that I send something and now I don't know whether it arrived to the other side or not, right? So what is the technique to deal with this? Because I cannot wait forever. So the only way is to add the timeout. So the response timeout is the technique to address the possibility for either packet loss or acknowledgement loss. Okay? So that's another level that we need to handle now, is to introduce a new event that, in addition to all of this, we need to also account for the fact that there might be a timeout. A timeout, it's another interrupt event. So when we send, we need to start the timer. Because if there is any possibility for packet loss, then I cannot wait forever. Because here, we assume that we wait forever. Because we assume, again, that the channel cannot lose anything. If the channel has the possibility of losing something, then I cannot send the packet and wait forever. Okay? So I have to wait for a certain period of time. Okay? طيب. So as we said here is that because for each packet we're waiting for acknowledgement and everything, this is just to explain that in this case we only need 2 sequence numbers, and we will see the disadvantage of this in a few minutes. So this is why that only 2 sequence numbers will be sufficient. Why? Because for every packet we are receiving an acknowledgement. We're not sending anything new unless we receive acknowledgement. Okay. So we, of course, with this assumption, we have twice as many states on both the sender and the receiver. At the sender, we have 4 states. At the receiver, we have 2 states. And we have handled all the events we have discussed. So now, we can get rid of the negative acknowledgement because of the fact that we have the sequence number. Okay? We can technically get rid of the negative acknowledgement. We only send positive acknowledgement if we send a sequence with the positive acknowledgement, which means that I'm sending acknowledgement for the last packet that I received correctly. I'm sending acknowledgement for whatever I have received correctly. This means that I'm implicitly sending a negative acknowledgement for anything that you are sending to me that I'm not expecting. So negative acknowledgement can be replaced by handling the duplicate acknowledgement. So if the sender receives 2 acknowledgements for the same packet, it will be equivalent to negative acknowledgement. So let's see how this happens. So instead of sending negative acknowledgement, receiver sends acknowledgement for the last packet. Okay? So if I receive a packet and it's an error, there's something wrong with it, and instead of sending negative acknowledgement, we send the acknowledgement of the previous one. So this technically means what? That the new one that you are sending to me, I cannot somehow recover it. Okay? But in that case, instead of supporting or providing negative acknowledgement, I have to put a sequence in the acknowledgement. Right? So we have one type of acknowledgement. We don't have negative acknowledgement, but now we have to introduce the sequence number in the acknowledgement. Okay? So if you're sending me packet 1, okay, and packet 1 is corrupted, what did I receive correctly? Packet 0, right? This is the last one that I received correctly. So send the acknowledgement for packet 0. And this will implicitly tell the sender that packet 1 did not arrive correctly. So it will retransmit.
So we will send packet 0 twice. When we receive the 0 and when we receive the one that is correct.
Yes, exactly. That's why I said duplicate acts are usually equivalent to negative acknowledgement. This is the rule. Yani. Duplicate act with the same sequence number is equivalent to the fact that the first one you received correctly, but the second one did not arrive correctly, which means that you are telling the sender, I received the previous one correctly. Okay, but this implicitly means that the next one was not received correctly, right? So sending duplicate acts is equivalent to negative acknowledgement. Why do we need to remove negative acknowledgement? Is to prepare the design for go back in, and as we will see, just by supporting one type of acknowledgement, we make the design easier, okay? And by acknowledging the previous one that you received correctly, this implicitly means that the new one was not received correctly. So this will be a good, it's easier design, and it's more homogeneous for the case of go back in, as we will see in a minute. So duplicate act at the sender results in the same action as negative acknowledgement. Okay? Type. So the exact same one that we have talked about, the only thing different now is the sequence that we send with the acknowledgement. Okay? So when we wait for the acknowledgement 0, and now we don't have to wait for negative acknowledgement. So this state has changed slightly, but because there is no possibility that we receive negative acknowledgement now. We wait for acknowledgement 0. If we receive acknowledgement 1, okay, this means at the sender side that I need to retransmit. But if we wait for acknowledgement 0 for what we have sent, but we receive acknowledgement 1, this means that a 0 was not received correctly, so I need to retransmit. Okay, so that's what this means. So by checking the sequence in the acknowledgement, I can perform the exact same functionality of negative acknowledgement. Why we're doing this? Because again, this sequence number, as we will see, will try to merge the states for 0 and 1 and increase the number of packets that we support, 0, 1, 2, 3, 4, and we will merge all of this into one state. Okay? And then we check the sequence number in the acknowledgement to recognize whether this is an actual acknowledgement or implicitly it means negative acknowledgement. Okay? So only if I'm waiting for acknowledgement 0 and I receive the acknowledgement and no corruption and it's really 0, so this number matches this. Only then I can switch to wait for packet 1, and then I trigger the below part. And in the below part, it's just a mirror of the upper part, but for the case of 1. Okay? So it's the exact same thing. So the only difference here is that we have added sequence number not only to the packet, but to the acknowledgement. By adding the sequence number to the acknowledgement, I can get rid of negative acknowledgement. Okay? Any question? Any confusion? Of course, there is a lot of confusion.
This for acknowledgement 1 comes from here, yes?
This is acknowledgement 1, yeah? Here?
This?
Yes?
Yeah. It is related to the acknowledgement, yes?
Right. Yeah, so the idea here is that if you are waiting for acknowledgement 0 and you get acknowledgement 1, there is a mismatch. If there is a mismatch, stick to your state. Because what you have received is due to some error.
Here it will wait this to retransmit?
Yes, of course. Yes. So when do I transition to another state? Only when I receive a packet and it's not corrupted and the sequence number matches. Only then I can switch to another state.
Can you explain the arrow that is from the receiver side that's going out? Is it going back to the sender?
Another state.
Here is the sender.
No, the receiver. And down?
No, here is not the receiver. It's still the sender, but for the...
It's called receiver. There's
Receiver.
an arrow.
Oh, okay. Oh, okay. Oh, no, it's my mistake. Wait for 0. Oh, okay. Ah, right. صح. You're right. You're perfectly right. Okay. So here, there is a split. The part above is for the sender, and it's only one half of the sender. Okay? It's one half of the sender because there is another half of this sender because this arrow, it goes to the other half of the sender. So still here, the sender has 4 states.
I thought it's only...
No. Still here, the sender has 4 states, but there is a cut. Okay, the sender here still has 4 states. So there is, because here there is 0 and there is 0. So the same 2 states still exist for the case when the sequence is 1. Okay, because it's the same. Here the slide only highlights the difference, and the only difference here is that the sequence number in the acknowledgement is added. In the previous finite state machine, I did not add any sequence number to the acknowledgement, but I had acknowledgement and negative acknowledgement. Okay, so here we got rid of this. So now, when I wait for acknowledgement 0, only when I receive the exact match and there is no corruption, then I switch to the other state. And I don't have to do anything specific. I just, خلاص, everything is good and I switch to the other state. This corresponds to the fact that here, when you wait for a call from above, then you send. You send with a packet sequence 0. Right? This is from the sender side. This is supposed to be received here as a call from below. Okay? So if I wait for 0 from below, if the packet arriving has a sequence number 0 and it's not corrupted and everything, then khalas, then I consider that everything is fine. Here the case when I wait for packet for packet 0 to arrive, but the packet that arrives has sequence number 1. When this happens, I extract. This is coming this way. Sorry, it's yeah. When the packet arrives is 0, then it triggers this arrow here. So there is no event or action. This is because this is cut. But the error states are if the packet arrives and it's corrupted or has a sequence number of 1. So it's either corrupted or has a sequence number of 1. So what happens here is that he merged both cases in the previous finite state machine. Why? Because in that case, we don't have two states, whether this is negative acknowledgement or positive acknowledgement. So we're only dealing with acknowledgement. So that's why he was able to merge the two cases into one. So if I received an, there is any corruption or the sequence number does not match. In both cases, what I need to do is that I will discard this packet. When I discard this packet, I will send the same acknowledgement again. So that's what this means. So here, I did not pay attention to the fact that he split this slide into two halves. One is the sender and one is the receiver. But that doesn't mean that this is the entire sender and this is the entire receiver. Still, for the sender, we have 4 states. And for the receiver, we have 2 states. But this is the part where we introduce changes. And the only change that we introduced here is the fact that the acknowledgement has a sequence number. Okay? So it only needs a little bit of follow-up to the arrows and understand what we have introduced new in this case, which is different from the previous one. So what we have introduced as a new thing here is the fact that we have introduced the sequence number in the acknowledgement. Okay? And the rule is, if I'm in a state to expect a packet with a sequence number, if I receive a packet with a different sequence number, then I discard. Okay? If I'm the receiver, I will send the acknowledgement for the previous one, which is the one that I received successfully. That's the main rule. Okay? Channel with error and loss. So until now, again, so what we need to recognize here is that what we need to add is the timeout. So logically, kida, when we think, we need to deal with the loss through the concept of response timeout. This is the simplest and the most common mechanism to deal with any packet loss. We're sending, we're not expecting when the acknowledgement will arrive. In that case, when we send, we cannot wait for acknowledgement forever because it may be lost. So we need to add the event of the timeout. Mashi? We'll have 5 minutes stretch and then we'll continue.
Office hours means
4 to 5.
4 to 5.
Again, if that's not convenient, then you can schedule something by, if you want another office hour in another day, just say that. And I can come at 4.
Office hours means on
I can come at 4 or 5 or 6 at any day, any other day. You agree on a day and I can come.
What is difficult for us since
So very quickly, if channels with error and loss, the new assumption now is that the underlying channel can also lose packets, in which case the checksum and acknowledgements are not enough. Okay? In which case, if I send something, I cannot wait forever. So the approach here is that when I send, I will wait for a reasonable amount of time. And reasonable here is actually a very important word. because we will quantify what this reasonable means. That's part of the analysis that we will do on TCP. So
Time to
how can...
time to learn.
No. The timeout. The timeout has some calculations in TCP. So we will analyze what this looks like. But for now, we just say reasonable. How reasonable? We don't know. Okay. So retransmit if no acknowledgement received. So if I don't receive an acknowledgement during this period, during this timeout period, this is as if we have received a negative acknowledgement. So this is equivalent to the fact that we receive negative acknowledgement. Or we assume that either the packet is lost or the acknowledgement is lost. Because again, the loss may happen on either direction. I sent a packet, okay, and the packet was lost. I sent a packet, it arrived, but the acknowledgement from the receiver was lost. Okay, so there are two possibilities here. In all cases, I'll wait for some time, then retransmit. If packet or acknowledgement that's just delayed, not lost, this case is interesting now. That's why we said reasonable time, because this reasonable time might be a premature. Okay, so I waited for some time, and then after this time is finished, okay, I need to retransmit. But actually, it's not that the packet or the acknowledgement were lost. They were only delayed. So this means that the timeout that I waited was not enough. So if I had waited for a longer time, I wouldn't have to retransmit. Okay? And we'll see this on the timeline. So if packet or acknowledgement just delayed, not lost, in which case the retransmission will be considered for the receiver a duplicate packet. But we know how to deal with duplicate packets. How? Sequence. Okay? So we have the sequence. So we can deal with that. Okay? So that's this issue is solved. So receiver must specify the sequence number in the packet being acknowledged. And we have done this before. So, so this case will be taken care of. So all we need now is just to start a timer. And this timer is countdown timer. A timer, it starts from a specific time and it counts down. Once it reaches to 0, then the timer is elapsed and we need to retransmit. So we see how this looks like. So it's the same 4-state sender. We see the differences now is that when we send, there is a start timer. Okay? So this is one change. We see a very interesting state here. We receive a packet. Okay, we are we are waiting for 0 from above, but we get a received packet from below. Okay, so we are waiting for a packet to arrive, but we receive we receive RDT receive, which is actually a packet that is coming from below. When does this happen?
The timer stop.
When the acknowledgement delay.
Delay, bravo Ali. When the acknowledgement is delayed. Because we are now trying to send a packet, but we receive a delayed acknowledgement. We will discard, we will not do anything. Because currently I'm waiting for a packet to be sent. So this acknowledgement is delayed, it's coming from previously, and I don't have to handle it. خلاص? Okay? So when I send, I will start timer. So if this timer elapses, so when I send, I will start the timer and I will go here. If this time elapses, then I will trigger the action off as if I received a negative acknowledgement. But the difference here is that I will start the timer again.
No, we are not clear, sir. Here we are sending and timer started. So timer started for acknowledgement, correct?
Right. So now I'm waiting for acknowledgement.
Right. But here, timeout, why this timeout and how this is linked to this one, and why this end is timed out. This I am not understanding, sir.
هو wait for acknowledgement. Acknowledgement 0. Okay. How long do I wait? Okay. I wait forever? No, I cannot do that. So there is a possibility that I receive acknowledgement in error, and we know how to deal with this. So here we receive, and it's corrupted, or the sequence number does not match, and we know in both cases we don't need to do anything. We just discard and that's it. Do I have to start a new timer? No, I did not. Yeah, so the previous timer did not elapse yet. So I don't have to start a new timer. Only when a timeout happens. A timeout, this is an interrupt. So the timer is a countdown. So this means that the timer has reached 0. Right?
Mm-hmm.
So the difference between this and this is that now I need to retransmit the packet and start a new timer. Okay? But if I receive a negative acknowledgement, of course, not negative, an acknowledgement for a previous sequence number, or if it's corrupted or anything, this is nothing. I don't have to do anything.
They drop them?
I drop them, but you don't do anything. You don't retransmit, you don't do anything until there is a timeout. Okay? Of course, one thing you may choose to do when you receive a corrupt or negative acknowledgement is to do what? To retransmit. So instead of doing nothing here, you may select to retransmit. You can do this depending on your choice. In fact, what are the chances here? You receive something in corruption, but this was actually an acknowledgement. So what will happen? You retransmit and it's a duplicate packet. The receiver will handle this. We know. But there is a possibility that what you were sending is an acknowledgement for the previous packet. So this tells me that you did not receive my current packet correctly. What is the point of waiting until a timeout? Okay? So if you put here retransmit or UDT send, that's correct. This is correct. Of course, there is a possibility that this will be a duplicate packet, but the receiver will handle it. We know that. But if the receiver is sending me a positive acknowledgement for the previous packet, so this means that the current packet was not, this is a clear indication from the receiver that the current packet was not received correctly. Okay? Here, this current implementation does not do anything, which means that, okay, the retransmission will be handled by the timeout. Okay? But as a designer, I may choose, okay, so why wait until there is a timeout? I might be proactive and retransmit.
You have to retransmit and start the timer again.
When I retransmit, if I choose to retransmit, I can start the timer again. Okay? But here, in this current implementation, the designer chose that I will not do anything, which means that the retransmission is handled by the timeout. Because either during the timeout, I will receive a positive acknowledgement that will match the sequence number. In this case, I will where's this case? I will stop the timer. Of course, when I receive a positive acknowledgement, I will stop the timer and I switch to the next state. Okay? Or I will not receive another acknowledgement which means I will time out. In the timeout, I will retransmit and I will send, I will start a new time. So this is the case. So the changes here are only the timeout. The timeout event is now a new event that we need to handle. And the timer is now a new parameter in the system that I need to start whenever I send a new packet, and I need to stop whenever I receive positive acknowledgement. So I start when I send a new packet, or I retransmit a new packet, or I retransmit the same packet again. Okay? And when I stop it when I receive positive acknowledgement. So this is good. So we understand the differences now. And this case. Okay? I was waiting for something to come from above, but I received something from below, which is weird. Okay, I received an acknowledgement that was it was not lost, it was delayed. Okay, so this is weird. So I will discard it. Of course, this is the bottom half is the duplicate, is again the mirror, as we have done before. So what are the possibility of losses? Here, this slide suggests that this is the happy path. For stop and wait, again, the sender sends, the receiver sends acknowledgement. And as long as the sender receives an acknowledgement that matches the sequence number of the packet, then it switches to the other packet. If the acknowledgement for any reason does not match, then we send the same packet again. So we know how to do this. This is the normal operation. If anything is lost, the loss can happen in the packet itself. If the packet is lost, then the sender will not receive any acknowledgement, of course, in which case the sender will time out. When it times out, it sends the same packet again. The one that's lost will send it again. And hopefully next time it will arrive correctly, in which case I will receive the acknowledgement and so on. So this is lost packet. Okay, so easy. Here is lost acknowledgement. So the packet has reached, but the acknowledgement was lost. So in this case, to me, it's the exact same thing. For the sender side, it's the same thing. It's slightly different for the receiver now. It will drop the duplicate packet. But it will send an acknowledgement for the previous packet that it was that it has received correctly. So when the packet 1 is sent, the acknowledgement is lost, in which case I will wait for a timeout, because to me I did not receive a positive acknowledgement. I will send the same packet again. When I send the same packet again, I will receive I will receive a packet, and now the packet is for the last one that the receiver received correctly, which is acknowledgement 1. So of course, the sender will say, oh, okay, I sent packet 1 before. So this means that the previous one, so the receiver will say, I received this before, I will drop it, and I will send an acknowledgement for the same one that I have received now, just now, okay? Which the case when we said duplicate acknowledgement is equivalent to negative acknowledgement.
The acknowledgement one that is lost, it has a different number than the one that is the new one, so that the sender distinguishes the difference between them. Like when it receives the new one, it will know that the other one was lost.
It will know that, so because packet 1 here is the same one that the receiver has received before. So for the receiver, I received packet 1 before. The receiver here is in which state? Is receiving packet 0 state. So packet 1 arrived, so the receiver will delete the duplicate, okay? And it will send acknowledgement. For what? For what it has received correctly. The receiver always sends acknowledgement for the last packet that it has received correctly. Okay?
But again, it is sending packet 0 after receiving acknowledgement 1. Sending packet 0?
Yes, of course, because now the sender has received successfully acknowledgement for packet 1, so it needs to go to the next one and
Next
send.
one is 0, 1, 0.
Yeah. We always go 0, 1, 0, 1. But there's no 2.
Okay.
We will talk about why we don't have 2 now. We will talk about this.
I thought it is again went back to the 0.
No. We always go 0, 1, 0, 1, 0, 1, 0, 1. Okay? Because again, we are still in stop and wait. This third case is interesting now. So let's look at this closely. So we sent packet 0. We received acknowledgement 0. So far, so good. We sent packet 1. It was not lost. Acknowledgement was not lost. And this is the case when this is the, remember this. So here, the receiver, sorry, the sender timed out prematurely. This indicates that the timeout calculation from the sender side was a little bit off record شوية. Okay, was premature. Okay, so it timed out prematurely. So the default procedure is that the sender will send the same packet again, will retransmit. And of course, this packet has arrived in the receiver before, so the receiver will discard and will send the same acknowledgement again, duplicate acknowledgement. This is from the sender side, from the receiver side. From the sender side, now that it has received this delayed acknowledgement, so so here it sent the packet 1 again. So here it's up to the sender now. Since it has received acknowledgement 1 that it was delayed, it may actually send packet 0 right away because packet 1 has arrived correctly at the receiver side, or it may wait for another timeout and retransmit. It's up to the sender. And here it receives the acknowledgement 1 and then it starts packet 0 again. Okay? So this one is actually the case of premature timeout, or we call it delayed acknowledgement. Okay? And in that case, it's already handled. Now there is an important calculation, and this is actually the motivation for go back n, as I said before, it's not from the error point of view, it's not from the reliable data transfer point of view, it's just from the performance point of view. Okay, so here we are talking about the fact that stop and wait, it works for all the cases for loss, for error on the channel, for delayed acknowledgement, losing packets, losing acknowledgement, it works, right? But the problem here is performance. To understand the performance, let's just talk about a simple example where we have a link of 1 gigabit per second. And here we have 15 millisecond propagation delay. Okay? So we have a channel. So you have a sender. So this is the sender. And this is the receiver. Okay? So 1 gigabit per second, this affects what? Affects the transmission delay. So if you have a packet with a length 8,000, this means that you have a transmission delay. The transmission delay is now 8,000 divided by 10 to the power 9. Okay? This is the transmission delay, which is around 8 microseconds, sorry. So the idea here is that the transmission time is very small. Remember, the transmission time is the time where you consume the channel itself. The problem here is that the propagation delay is 15 milliseconds, which is a lot more than the transmission delay. This indicates what? You transmit for 8 microseconds, and you spend 15 milliseconds, okay, to reach this packet to the other end. When the receiver sends you the acknowledgement, it will take another 15 milliseconds to arrive back to you. Okay? So how long did you actually consume the channel?
30,
8 microseconds.
What was the question?
How long have you actually used the channel effectively?
Effectively.
Ah, used it to send something.
correct,
8
8 microseconds.
microseconds. How long did you have to wait? 30 plus 8 microseconds. Okay? So the channel utilization here is the 8 microsecond, or the transmission delay divided by the total transmission plus propagation. So the problem here is that because of the fact that the propagation delay is very long and the transmission delay is very small. By the way, this is the common case on the internet, because the propagation delay here is actually the time that it takes to reach from one application to the remote application. Okay? The transmission time is when the sender finishes sending the packet on the medium. So that's very small. That's very, very small. If we have 1 gigabit per second, it's actually very small. The sender finished transmitting, okay? But the problem is that the time that this packet will take to reach all the way to China, let's say, and come back with an acknowledgement is very, very long, okay? So the effective utilization of the channel is actually the actual transmission delay divided by the total delay. Yeah, this is how much I actually use the channel, okay? But this is how much I waited. This is coming from the fact that you use stop and wait. Because we have to wait for an acknowledgement before we start sending another packet. Okay? So how long did we have to wait? 30 milliseconds plus 8 microseconds. How much did we use the channel for? Only 8 microseconds. So the utilization here is a very, very, very small. It's 0.027%.
Did we use the 8 milliseconds or the 0.027%?
Hmm?
That we used this line, that we used it, is it the 8 milliseconds?
8 microseconds.
Microseconds, which is corresponding to, what is the utilization?
This is the utilization from the sender point of view. This is the channel utilization. Channel utilization is the amount of time that I have effectively used the channel divided by the total amount of time, okay, which corresponds to the propagation time plus the transmission time. This is the utilization of the channel, which is very low. So we want to be able to يعني, utilize the channel for more than this without having to wait. Which means that we need to be able to send many, many, many packets without having to wait for acknowledgement. Okay?
After only 150, how did 15 milliseconds, how did it come twice? Only one propagation delay.
Propagation delay, yes, because between the sender and the receiver, remember, between the sender and the receiver, there could be many routers, right? So these routers introduce some delays to the packet. So to me, here, the propagation delay is an abstract end-to-end delay, okay, between all the routers. By the time the packet passes all the routers to go to the actual receiver, and then the receiver will send me an acknowledgement, which will take another 15 milliseconds to come back. Okay, I waited for 30 milliseconds, but I actually used the channel only for 8 microseconds. So the utilization here is very low. So we want to be able to increase this utilization. In which case, if I were to have the mechanism of sending, let's say, 3 packets, okay, without having to wait for acknowledgement, which cannot work with stop and wait. Stop and wait cannot do this, right? But if I have the mechanism to be able to send 3 packets, then this utilization will be multiplied by 3. على طول. So I used the channel for 3 transmissions consecutive Okay? And I didn't have to wait. I waited for one acknowledgement, and this is given the fact that this acknowledgement will be accumulative for all of them. So I sent 3 packets, and somehow the receiver received all these 3 packets and sent me one acknowledgement for all of them. If that's the case, then the utilization will be multiplied by 3. So imagine if this is like 50 packets, so this utilization can be raised up. But this requires even a more complicated mechanism, more than what we have talked on so far.
If one of the 3 packets is lost,
Is it?
If one of the 3 packets is lost,
Oh, it's lost? Okay, then it's okay. It's not counted in this utilization. So on the average, we were saying that, assuming that this is, all the packets are correct.
I mean, the acknowledgement will not be sent, right? It should receive.
Of course. Oh, of course. This is how go back in works. So if I send 3 packets and the packet in the middle is lost for some reason, then our rule for acknowledgement is always to send acknowledgement for the last successfully received packet in order. Okay? So packet 0 arrived correctly. Packet 1 lost. Packet 2 arrived correctly. Send acknowledgement A, 0. We'll see that. We'll talk about this. But the idea here, or the motivation, is that if we were to have the mechanism to accommodate multiple packets to be sent without having to wait for acknowledgement, this will raise the channel utilization. Okay? ماشي? So we'll stop here just to give the chance to Ranim to